channel routing algorithms in our last class. So, if you recall, the algorithms that we had looked at are the basic left edge algorithm and one of its extensions. Now, in the basic left edge algorithm, the nets were considered to be assigned to tracks starting from the leftmost boundary of the nets, and in that sorted order the nets were considered. Now, in the basic left edge algorithm, we had assumed that there are no vertical constraints, but in practice there will be vertical constraints. So, means one particular terminal of one net may lie just above the terminal of another net. So, in general there will be vertical constraints, and we had looked at an extension or a modification of the basic left edge algorithm where vertical constraints were also present. Now, there the idea or the consideration was that if there is an edge in the vertical constraint graph from net I to net j, then net I must be considered first and then net j. So, in terms of the vertical constraint graph, just by looking at the direction of the edges, we can also find out an ordering, just not necessarily only based on the left edge of the nets, also on the direction of the arrows, that which of the net has to be considered before the other. So, with these two modifications, we were able to route a net where there were some vertical constraints. But one restriction was there in the solution that we had obtained, is that whichever algorithm we are using, any one of the two, say a particular net was assigned totally to a single track. So, there is no concept that one net would be broken up and the two or three horizontal segments of that net would be assigned to different tracks. That was not the concept. The entire net was assigned to a particular track. Okay. So, the algorithm that we will be considering first today, that can relax that restriction. There you may allow breaking up of the horizontal segments of a net across several tracks. Okay. So, this routing algorithm that we will be looking at, this conventionally is called Dogleg Router, because whenever we break a horizontal segment of a net across more than one tracks, it is called a dogleg. So, the basic dogleg router tries to overcome the drawbacks of the left edge algorithm that we have just mentioned, namely the entire net is assigned to a single track. But in fact, it can be easily proved that in the absence of any vertical constraint, this basic left edge algorithm gives you the optimal solution in terms of the number of tracks required. But if there are vertical constraints, then optimality cannot be guaranteed. That we will see through an example shortly. So, in the presence of vertical constraint, you may get a routing solution using the left edge algorithm which takes more number of tracks than the optimal solution. So, this is one motivation where we can possibly look for an algorithm which can break a net across tracks. Say a particular net, instead of routing like this, we may route it like this, maybe. So, this is what is called a dogleg, we had mentioned earlier. So, in a dogleg, the basic idea is you are placing or allocating parts of the same net on different tracks. So, when you have parts of the same net on different tracks, then there will be some vertical segments on the other layer which will be joining these two, obviously. So, actually these vertical segments are called the dogleg connections. Doglegs are the vertical segments of the wire which will be connecting these two trunks which are located on two different tracks. Now, we will see through an example that this may sometimes lead to a reduction in channel height, okay, the total number of tracks you require. to complete the routing. So, the routing algorithm that we would be looking at, this allows multi-terminal nets. Of course, the left edge algorithm also allows multi-terminal nets, but here also we allow multi-terminal nets and vertical constraints as well. Now in the algorithm, if you have a multi-terminal net, it gets broken up into a series of two terminal nets. For instance, if you have a case where you have a terminal, say 1 out here, 1 here and 1 here, this will be broken up into actually two nets. First one will be starting here and ending here, the second one will be starting here and ending here. Starting from the leftmost boundary, as you go on sequentially scanning the terminals of the net from left to right, so you take the two terminal nets which come in the way and you will just break it up in that way. So, if there are 4 terminals, there will be 3 such two terminal nets, one after the other. But one restriction of the algorithm that we will be presenting is that it cannot handle cycles in the vertical constraint graph. Okay? Well, so now let us first take an example which will show you that how the use of doglegs can reduce the number of channels required, tracks required. So, a very simple example. So, let us take a channel routing problem like this, where there are 3 nets 1, 2 and 3. So, as you can see, the net 1 starts from here and spans up to here. Net 2, it starts from here and spans till here, and net 3 starts here and ends here. And if you look at the vertical constraint, there is a constraint between 1 and 2. So, there will be one arc between net 1 and net 2. There will be another arc from net 2 to net 3. So, there is a directed path in the VCG from 1 to 3. Well, now if we allow the extended left edge algorithm honoring this ordering of the VCG, then obviously 1 has to be done first, then 2 and then 3, you have no other choice, because there are directed arrows from 1 to 2 and 2 to 3. So, first when you assign 1, you assign it to the first available track. 2, well, you can only assign the second track to it because this is already occupied. 3 again, well, you can see well, there is another terminal here, I have not shown this, there will be a connection here also. So, due to this connection, you cannot assign the net 3 to track 1, you have to assign a new track to it, right. So, this is a solution which requires 3 tracks. Now, one result follows from this example is that if you have this kind of a directed path in the VCG, and if you say that I will not break up a net across tracks, then the length of the path, maximum length of the path in the VCG, that also will give you a lower bound to the number of tracks required. Well, the one bound comes from the horizontal constraint graph, you take the size of the maximal subgraph, the clique, that will give you the number of tracks required minimum, and again if you look at the path length in VCG, that will also give you a lower bound. But the same solution, if you allow a net to be split across tracks, then we can get a solution like this. Here net 1 as usual is placed on track 1, net 3 is as usual placed on another track, but net 2 instead of placing as a whole on one track, in which case a new track was required, if you break it up like this, then you can say you can do with 2 tracks only. So, a part of net 2 is assigned to the same track as 3 and a part of net 2 is assigned the same track as 1. So, here you have a dogleg, this is the dogleg junction. So, doglegs can reduce the density of the channel in terms of the number of tracks. This simple example illustrates.
So
Yes.
in your example, we can have 2 tracks without having doglegs.
In this example, you can have 2 tracks without having
So the 3, the
this
track
one.
number 3, so let
Yes, yes.
track number 3 shifted to track 1.
In that case, there will be a conflict between 2 and 3. There is a connection to 3 and 2 also. There will be a short circuit here,
So there's a connection.
just due to that. So, if this 3 was not there, you could have done that. Okay. Fine. Now, okay, this example gives you the motivation why dogleg is used, means how it can reduce the number of tracks. Well, this is from the view of optimization of the solution, but there are certain situations where dogleg is mandatory. But although the algorithm we will be considering right now that does not consider that scenario, but let me also talk about that scenario where there is a cycle in VCG. Now, the basic dogleg algorithm we are considering right now that cannot handle cycles. So, let us take a simple routing problem, a channel routing problem with nets placed like this. So, as you can see in VCG there is a path from 1 to 2, there is a path from 3 to 1, there is a path from 2 to 3. So, there is a cycle. Now, in terms of the solution, if you try to apply the basic left edge algorithm, then well just ignore the VCG for the timing. Suppose you try to assign to the tracks, say you first route net 1, then say you route net 2, but while routing net 3 you will end up into a problem. You cannot assign net 3 into a single track, because there will be either conflict or there will be short circuit with this net or there will be short circuit with this net. So, what you can do, there are actually 2 alternatives. You can either have, if you have a spare column in between, then you can either have a solution like this with another track and a dogleg. So, in this case you require 3 tracks, 1, 2 and 3, or if you do not have a spare column in between, okay, sorry, 4 track, for this 2, 3 and 4, right. So, there are 4 tracks which are required. This you can do provided you have a free terminal column, a free column in between. But if the pins are already packed, there is no free column in between, then you will have to do something like this: 1, 3, 2, 2, 1, 3. Then the first 2 nets will be routed as usual: 1, 2, 1, 2, 2, 2. Okay. There will be dogleg again, no doubt, but the dogleg will now be put like this. There will be an additional column which will be taken up at the end of the channel. So, if you have a space in between, you can use that, or you will have to extend the net towards the right or towards the left and reach the end of the channel and use up an additional column out there. Okay. So, there are some algorithms that we will be seeing later which can take care of this kind of a scenario, but the basic dogleg algorithm we will be looking at now, that does not take into account cycles in VCG, right. Okay. So, the basic algorithm works like this. Well, of course, if there is a cycle in the VCG, this algorithm cannot handle it. So, you will be returning with failure, you cannot route it. Step 2, as I had mentioned, if you have a multi-terminal net, you break it up into a sequence of 2 terminal nets. Well, the way you do it is like this. Suppose you, well, just in terms of the horizontal direction I am showing, suppose this is the horizontal span of a net and these are the different terminal positions either on top or on bottom, say here, here, here and here. Suppose this is the span corresponding to net number 2. So, in the original sub problem all these terminals were labeled as 2, 2, 2 and 2. Now, when you split it up, you call this net segment as 2A, call this as 2B, call this as 2C, which means for the first segment the pair of terminals will be labeled as 2A and 2A. For the second segment it will be labeled as 2B and 2B. So, some of the common terminal will be sometimes called 2A, sometimes called 2B. Similarly, the third segment will be called 2C and 2C. So, if you have a multi-terminal net, you break it up into a sequence of 2 terminal nets. So, 2, 2, 2 will be broken up into 2A, 2A. This 2A and 2B are actually the same terminal. You are assigned 2 different terminals. I will give an example shortly. And after you do this, you apply the extended left edge algorithm. See, once you have broken this up like this, what you get? Well, let us take an example, then I will tell you. Take this. This is a simple example where the vertical constraint graph looks like this. There is an edge from 1 to 2, 2 to 3 and 4 to 3. This is the VCG. Now, here you see that there are some nets which are multi-terminal. One is this net number 2, where you have a terminal out here, you have a terminal out here, you have a terminal out here. This is your net number 2. Similarly, you have net number 3, which has a terminal out here, a terminal out here and a terminal out here, and net number 4. Net number 4 is like this, here, here and here. So, here all these nets 2, 3 and 4, these are multi-terminal nets. So, as per our strategy, we break these nets up into individual 2 terminal nets, like this net 2, 2 and 2 we break up into 2A, 2A and 2B, 2B. So, actually now there are 2 different nets, one is 2A like this, one is 2B like this. Of course, 2A and 2B touch at a terminal obviously. Similarly, net 3, 3A and 3A and 3B and 3B. Similarly, 4, 4A and 4A, 4B and 4B. Now, as we do this renumbering, our VCG also gets modified. So, now the constraint will be 1 to 2A, 2B to 3A, 4A to 3A and 4A to 3B both, that is all. So, our VCG also gets modified. But once you do this, what you gain is that now since we have split this net 2 into 2 different segments 2A and 2B, and these 2 net segments are treated independently. So, when you apply the left edge algorithm, you can possibly assign 2A and 2B to 2 different tracks. That is the idea. But here, although I have not shown the horizontal constraint graph, normally if 2 nets are like this, which start and end at a particular column position, there will be a horizontal constraint between them, they cannot be put on the same track. But since 2A and 2B actually belong to the same net, there will be no horizontal constraint between 2A and 2B. That is the only one change you make in the HCG. So, I am just noting it down. In HCG, in horizontal constraint graph, there will be no edge between say 2A and 2B, as an example I am taking. Similarly, between 3A, 3B and between 4A, 4B. Because if the need arises, 2A and 2B can also be placed on the same track. Okay. But if they belong to 2 disjoint nets, you could not have done that. Okay. Fine. So, once you do this, for this problem, if you apply the extended left edge algorithm, the solution comes like this. Start from left to right, you just again look back at the constraint graph just to see in which order you have to consider. Look at the constraint graph, 1, 2b and 4a are the ones which do not have any incoming edges, okay. But once you finish 1, you can also start with 2a. So, here from the left edge net 1 comes first. So, you assign net 1 to first track, this is your track 1. Well, once net 1 is completed, net 2a is ready. 2a cannot be assigned to the same track because there is a horizontal constraint between 1 and 2a, they belong to different nets. So, 2a will be assigned to the second track, this is track 2. Well, once you have done 2a, you can also do 2b because 2b also does not have any constraint, 2b can be started. Now, according to the left edge algorithm, you will be assigning 2b to the first available track. So, 2b will not be assigned to track 2, rather it will be assigned to track 1, 2b will be assigned here. Next will come, so after 2b you see, once 2b is done, you can start with 4a because 3a and 3b cannot be started, 4a is the first you have to take. So, after 2b you will have to take 4a, this is the first net you have to take. So, this will again be assigned to the first available track T1, 4a up to here. Well, 4b does not have any constraint, 4b can be taken up any time, but now you can take up 3a and 3b. 3a cannot be assigned first track because 4a has already been laid here, 3a has to be assigned to track 2, similarly 3b. 4b there is no constraint, you put it on the first available track T1, then you join the nets, this will be the final solution. So, you see in the final solution some of the nets are not split across tracks, but some of the nets are. So, the basic Dogleg algorithm tries to minimize the number of channels by putting the different segments of the same net across tracks. This is the basic idea. Okay. So, in the absence of cycles in the VCG, this method works pretty well, right. Okay. But the problem in this method is that, well, if you have many nets with multi-terminal pins, then the number of nets you have to consider in the modified problem, that goes up quite considerably. The number of these split nets become pretty high, because ultimately we are applying the left edge algorithm, the number of nets you have to consider there will be high, large. So, there is another algorithm which we will be presenting now, that gives a good solution, but that does not consider dogleg. Without dogleg, that gives you a fairly good solution. This is a pretty well known method. This is called net merge router. This was initially proposed by Wishimura and Ku. Well, now as the name implies, net merge, here the idea is that some of the nets were trying to merge. Well, what is the basic idea? Suppose I have net I and net j. There are some constraints. If net I and net j satisfy those constraints, we can merge them into one composite net or super net, whatever you call. So, after merging, net I and net j will become a single composite net. So, in this way, we would be continuing to do this merging as far as possible. Now, after merging, what will happen is that a composite net will have to be placed on a single track. So, instead of considering the individual nets and let the left edge algorithm spend a lot of time to assign them to the tracks, now a composite net will be assigned to a track. Now, when we assign a composite net to a track, all the individual nets that belong to that composite will automatically be assigned to the same track. This is the basic idea behind the method. So, let us see how it works. Now, this starts from the premise which I have just mentioned some time back, that if there is a directed path in the VCG of length p, then in any solution where you are not using dogleg, you will need at least p number of tracks. This of course provided you are not allowing doglegs, but if you allow doglegs it can be less. Now, in the net merge router, we are trying to merge nets in the way we have just mentioned, but we are always trying to minimize the longest path in the resultant VCG, because when you merge, the VCG also will get modified. So, we are trying to minimize the longest path in the VCG, and the process successively merges the nodes of the graph in order to achieve this objective. So, as I mentioned, this does not allow doglegs or cycles in the VCG. So, this you can consider this is another extension to the left edge algorithm, basic left edge algorithm. Okay. So, the way it works is this like this. This will partition the routing channel into a number of regions which are called zones. Routing channel means this is the routing channel. So, the pins are located on top and bottom. So, we can make some vertical slices of this sub problem, and this you can call zone 1, zone 2, zone 3 like this. And when you are saying that we are merging nets, well, we cannot merge two nets which belong to the same zone, because they will lead to a horizontal constraint then. Nets will be belonging to the same zone if there is horizontal constraint between them, their left edge and right edges or the spans overlap. So, we can merge two nets which belong to adjacent zones, right. And as I said, once you merge them, the merged nets will be treated as composite nets, and when you allot them to the tracks, the composite net will be assigned to a single track. So, now let us see how this zone definition is carried out and how we can use this to merge the nodes and assign them to tracks. Okay. So, in this algorithm there are three steps essentially. The steps are, of course, the first step is to identify the zones, zone representation, and once you identify the zones, you can start merging the nets, and once you have finished merging them, you can assign the composite nets into tracks. These are the three steps. Yes.
Does a composite net consist of integral number of nets? I mean, can be a net, half of the net belonging to this composite net, half of the net belonging
Well,
to
a composite net will always consist of a number of nets in its entirety. You cannot break up a net and say that half of this belong to this and half of this belong to that. Well, this is because we are saying that we are not allowing any dogleg. A net will always be put on a single track. Okay. Now, as an example, we take a slightly complex example where there are, you can see there are 10 nets which are placed like this, and these lines show the span of the nets. This is the span of net number 1, this is net number 2, this is net number 3, this is net number 4, this is 5, this is 6, this is 7, 8, 9 and 10. So, you see that you have so many nets, there are 10 nets. Now, the first thing is that let us carry out an exercise that from this example, let us try to construct the horizontal constraint graph. You just look at the overlap, say from node number 1, this is the span. So, it overlaps with 2, 3, 4 and 5. So, there will be edges to 2, to 3, to 4 and say to 5. So, from net 1 these are the edges. From net 2 in addition you have edges with 6. So, 2 will be having an edge with 3, with 4, with 5 and with 6 also. Net 3 will be having edge with 2, okay, 2 already you have taken, 4, 5, nothing else, 4 and 5. Net 4 will be having an edge with 5 and with 7, 8 and 9. 7, 8 and 9, 6 also, okay, 6 also. So, net 4 will be having an edge with 6 also. Similarly, 5 we have already taken, 6 will be having an edge with 7, 6 and 7. 7 will be having an edge with 8, 9 and 10, 8, 9 and 10. 8 will be having with 9, not with 10, 8 and 9 and 9 and 10. Okay, so, this is the horizontal constraint graph for the problem. Now, if you analyze the horizontal constraint graph, you will observe one thing, that in this graph there are certain maximal complete subgraph or cliques. For instance, this subgraph consists of nodes 1, 2, 3, 4 and 5. This is a clique. All these nodes are connected to all others. Similarly, you see I think I missed one edge. There will be an edge between 4 and 6. So, I did not draw that between 4 and drawn it already. So, you see 2, 4 and 6, this will be another clique. So, there one clique is 1, 2, 3, 4, 5 maximal complete subgraph. See 2, 4 and 6, there is a triangle here. This is another maximally complete subgraph. There is another maximally complete subgraph consists of 4, 6 and 7. This is another triangle, 4, 6 and 7. There is another consists of 4, 7, 8, 9, this one, 4, 7, 8, 9 and lastly there will be one 7, 9 and 10. Okay. So, for this HCG, these are the different cliques or maximal complete subgraphs. Now, the idea is that if you have a maximal complete subgraph, say 1, 2, 3, 4, 5, then nets 1, 2, 3, 4 and 5 must be placed on different tracks. Well, if we decide not to break them. Okay. Well, now the way we are defining zones, it comes directly from the horizontal constraint graph representation. These cliques indicate the zones. Okay. So, let us see how the zones are defined. Well, we have a channel routing problem. There are a number of columns. Okay. These are the columns which correspond to the terminal locations, say column 1, column 2, column 3, column 4 and so on. So, whenever you look at a particular column, for example, let us take that example once again. Say if you look at this particular column, column 4. Column 4, you see your column number 4 intersects net 1, net 4, net 5, net 3 and net 2, 5 nets. So, each column will be intersecting some nets that we denote by this set Si. This SI will denote the set of nets whose horizontal segments will intersect column I of the channel. Okay. Now, as we go on computing SI, you will find that, well, some of the SIs can be subset of others. So, we take only the maximal SIs which are not subset of others. You take only those SIs which are maximal, not a proper subset of some other SJ. Now, if two SIs are identical, you take one of them, delete other, and if one is a proper subset, delete that proper subset. Take only the maximal ones. So, after taking the maximal ones, whatever remains will be these. This is the idea. So, if you look at this problem once more, say as you scan from the start, column 1, 2, column 2, 1 and 3, no sorry 1, 2 and 3, column 3, 1, 4, 5, 3, 2, in this way it goes on. So, I will just show this. Now, once you have identified these maximal SIs, you call or treat each of them as a zone and assign a number to the zone 1, 2, 3, 4, 5 in that order. Now, from the horizontal constraint graph, we have identified these clicks, and these clicks indicate the zones. There is an alternate representation of horizontal constraint graph, we shall show it shortly. This is called an interval graph. Now, in the HCG, as it is just shown, a zone corresponds to a maximal click. Well, a click is maximal, of course. Now, let us see what interval graph is and the zone definition for the problem we have taken. Okay. This particular slide will show you that as we go along the columns of the problem, for the example we have just taken, what are the values of SIs? This you can correlate to that example later, but I am just showing this. In column 1 only net 2 is crossing, column 2 1, 2, 3, column 3 1, 2, 3, 4, 5 in this way, 1, 2, 4, 5, column 6 2, 4, 6 in this way up to column 12 you get. Now, once you have this list, you will see that across a set of consecutive columns, all these sets will be subset of some set there, and you identify that bunch as a zone. This will be your first zone. This 1, 2, 3, 4, 5 is the maximal subset out here. Now, as we move from 5 to 6, you will see that a new net is encountering. So, there is no subset relationship between this and this. So, here a new zone will start. Similarly, for column 7, some other 7 is coming in. So, neither of this can be a subset of the other. So, this in itself will be a zone. Similarly, this in itself will be a zone. From 8 again another net 8 starts, but 8, 9, 10, well, this 8 remains, a new net gets added. So, it is a subset of this. So, here this is the maximal, this is your zone 4. Similarly, for the last one 7, 9, 10 and then 9, 10. So, this is maximal. So, there are 5 zones which get defined corresponding to the maximal SIs corresponding to the different, you can say, set of consecutive columns. Now, this information you can depict in the form of a zone table. This is also called an interval graph. Now, in this table you define these zones 1, 2, 3, 4, 5. Now, each zone you show which are the nets which belong to that zone. In zone 1 you have nets 1, 2, 3, 4, 5, 1, 2, 3, 4 and 5. In zone 2 you have 2 and 4 and 6 is a new one. So, 2 gets extended, 4 gets extended and 6 is a new net which starts, but 1 and 3 does not extend to Z2. Similarly, zone 3 you have 4 and 6, but not 2. 2 will not extend, but 4 and 6 will extend. 7 is the new node which starts, new net which starts. So, in a similar way you can complete this representation. Now, this is another way of looking at the HCG and the zone information. So, from here you can know that in each particular zone which are the nets which are in conflict in terms of the horizontal spans. Zone 1 contains nets 1, 2, 3, 4, 5. This means that 1, 2, 3, 4, 5, these 5 nets must be allocated to 5 different tracks. Zone 2 says 2, 4, 6, which means 2, 4, 6 must be allocated to 3 different tracks. Zone by zone, this will give you an idea. The maximal information from each zone, and we use that information in taking the decision, because anyway we have decided not to split a net, right? Yes.
So zone 2 also contains net 2 and 4.
2 and 4, yeah, 2 and 4 gets extended, yes. Okay. And for the problem, the vertical constraint graph is also shown for the same problem. Here, as you can see that the maximal path length is 3. So, according to the VCG, minimum 3 tracks are required. Of course, HCG demands more tracks, but according to VCG, minimum 4 tracks are required, 10, then 7, then 6, then 2. There is a path of length 4. Okay. So, the first step is the zone definition. This is how you define the zones. The second step is the merging of the nets. Now, after you have defined the zones, now systematically we will be proceeding with the merging of the nets. Now, let us see how we can merge. Suppose we have a pair of nets Ni and Nj. So, 2 nets Ni and Nj can be merged if these two conditions are satisfied. There is no conflict between them in terms of HCG, which means they do not belong to the same zone. Okay. Secondly, there is no directed path between them in the VCG, because in the vertical constraint graph, if there is a directed path, which means that one has to be placed above the other. So, there is a constraint. So, if there are no such constraints, you can put them, merge them, so as to finally you can allot them the same track. Okay. So, if a pair of nets they satisfy these two conditions, then you can merge them together to form a so called composite net. Now, once you have merged them, you will have to modify the VCG and also the HCG or the zone representation, whatever you call. Well, I will be showing the VCG stepwise, HCG will also be similar. In the VCG, what we do, this the vertices Vi and Vj, which corresponded to nets Ni and Nj, will now get merged into a single vertex Vij. Similarly, in terms of the HCG or the zone representation, you will be replacing the two vertices by a net Vi dash j, that means I to j. Like what I mean to say is that, suppose in this example, so let us take this zone representation once more. Suppose in this example we have decided, say, to merge nets 2 and 8. Suppose 2 and 8 are the nets we will be merging. So, although there is a gap in between, does not matter, in the modified zone representation we will be having a single line, these two will not be there, we will be calling them 2 to 8. Okay. So, this will represent the composite net which starts here and ends here. This is how we will be modifying the zone representation. Okay. So, net merging is done for two nets which satisfy this condition, and this process is iterative. We continue doing it in an iterative fashion, where pairs of nodes are successively merged. Well, here there is a heuristic. There can be several pairs of nodes which you can merge, but the heuristic says that you merge that pair of nodes for which the increase in length in the maximal path in the VCG is minimum. Well, the ideal case or the ideal scenario will say that you try to minimize the length of the maximum path in VCG, but sometimes you will see that when you merge two nodes, the length of the path can increase a little bit, that you will have to allow. But even if it increases a little bit, you try to take that combination where the increase is the minimum, because in most practical scenario in VCG the path increase by a little bit can be tolerated, because a greater constraint comes from the horizontal constraints. Like in the example I have shown, the HCG has a click of length 5, which tells you require minimum 5 tracks. VCG has a path of length 4, which says you require minimum 4 tracks. So you have one flexibility. You can increase it by 1 without increasing the cost of the solution. Okay. So, if you have multiple choices, you merge that net pair, well, that you can say minimizes the length of the longest path in the VCG. Now, in fact, it can go up. In that case, you select the one for which the increase in length is the minimum. I will take an example to show it. But there is an interesting result. Of course, this result is not difficult to just prove. This says that if your original constraint graph does not have any cycle, then even if you merge two nodes, there cannot be any cycles, because in the VCG you can merge two nodes only if there is no directed path from one to the other. So, you just think over this problem. If you merge two such nodes with no directed path, there can never be cycles in the resultant VCG, right. Okay. So, let us again come back to that example. Let us show the steps of the algorithm. Okay. This was the original VCG. Just look at the original VCG. Now, these are the horizontal constraints zones, and this is the VCG. Now, in terms of the original constraints, the pair of nodes that you can merge here are 1 and 6. I am just showing you 1 and 6, they do not have any constraint horizontally or vertically. 3 or 6, 3 or 6 does not have any horizontal constraints, vertically also there is no directed edge, and 5 and 6 similar, 5 and 6. These are the three possibilities we have. Okay. Now, with respect to this graph, we can see that how we can merge the node. Let us see. Suppose we have this VCG and we decide to merge 1 and 6, 1 and 6. So, if you merge 1 and 6, I am only showing the VCG. The VCG will become like this. 1 and 6 will get merged, the remaining part remains unaltered, but from 6 there was an edge out to 2. So, now from 1.6 there will be an edge out to 2. Similarly, there was an edge from 7 to 6, now there will be an edge from 7 to this 1.6. So, the edges which are going out of 1 and 6, they will now be going out of 1.6, and the edges which are coming into 1 or 6 will now coming into this composite node, right. So, in this slide I am showing all the three possibilities. Well, if you merge 1 6, this is the resultant VCG. Well, I am showing the VCGs, okay, these are all VCGs. If you merge 3 and 6, this is the resultant VCG, and if you combine 5 and 6, this is the result. Well, now you have to take a decision out of these 3 which is the best. Now you evaluate with respect to the longest path again. In this one, the longest path will be starting from 10, 1, 2, 3, 4. 4 means there will be 5 nodes, 4 edges. Here again starting from 10, 1, 2, 3, 3, which comprises of 4 nodes, 3 edges. Here only 2 edges and 3 nodes. So, in terms of our heuristic, this is the best choice. So, in the first step of the iteration, we will be merging nodes 5 and 6. Okay. Now, after merging, your VCG gets modified to this. Your zone representation also gets modified by merging this 5 6 into a composite net. So, you repeat this process. Now, in the second step, you will see that you can merge you can merge 1 and 7, you can merge 5 6 with 9, you can merge 3 and 8. Well, I am not showing all these all the possibilities now. Here, from here you can merge 1 and 7, you can merge this composite net 5 6 with 9, you can merge 3 with 8. Well, in fact, you can also merge 4 with 10. There are 4 possibilities.
You have to check out the horizontal constraints also.
Yes, you will also have to check the horizontal. I am not showing this, but you will also have to continuously look at this graph. So, after merging, what is the condition, whether there is any constraint there also. Yes.
So, in this, like first of all, there's a if notification.
Okay.
So, like the zone 3 did not contain net 2 or 2.
Yes.
2 or 8.
Yes.
But now, after merging, it contains.
Merging it contains. Yes. Yes. So, once you have decided to merge 2 nets, the entire span gets reserved. So, now you cannot put anything else in between. It is true. Well, now again you do these things, all these 4 possibilities you try to merge and see which is the best. Well, I am only showing you the best paths now. So, the next step you will find that merging 1 and 7 will give you the best alternative. So, I am showing the steps here. So, in the second step 1 and 7 gets merged. This is the modified VCG. Well, here actually in the between I have skipped one step. So, actually after this step you will find that 5 6 9 or 3 8 they gives you the best cost. So, you can apply one after the other. So, I have applied both of them one by one, and this is the resultant VCG, where 3 and 8 have been merged, and also 5 6 and 9. This is the VCG. Now, again in the next step you will see that 4 and 10 can be merged. So, after you merge 4 and 10, this will be the resultant graph, and here you cannot merge anything any further. There will be constraint coming either vertically or horizontally. There is some vertical constraint, and between 2 and 3 8 there is a horizontal constraint. These two also you cannot merge. So, once you have arrived at a graph where you cannot merge the nodes any further, okay, there you have arrived at a possibility where each of these composite nodes can be allocated to a separate track. That is your, and based on these arrows you apply a left edge algorithm to allocate the tracks. First 4 10, then 1 7, then 5 6 9, then either this or this, any order. So, the third step is the track assignment. So, each node is assigned a track. So, actually we apply the left edge algorithm subject to the constraints. This is the ordering, and in terms of the tracks, just following the graph you allocate nets in this order. So, I am showing the final solution. This gives the final solution wherein track 1 4 and 10 are assigned, track 2 1 7, track 3 5 6 9, track 4 2 only 2, track 5 3 and 8. This will be final solution. So, the idea of this algorithm is this: you take your HCG, VCG and you constantly go on merging nodes based on some criteria, and finally apply the simple left edge algorithm to assign the composite nets to tracks. But in our next lecture, we will be looking at an algorithm which can finally take care of cycles in the VCG. We have not yet looked at any scheme where the cycles can be handled. Okay. So, this we shall be discussing next class.